タイトルを、Hypersurfaces in Symmetric Space.
Yeah, so yesterday I talked about mainly hypersurfaces with constant principal curvatures in the space forms over real numbers and complex numbers. So these are the spheres, complex projective spaces, and the real and complex hyperbolic spaces. And this was the last slide from yesterday, which probably confused most of you. So I want to continue a little bit with the discussing this, what is known in the space forms over the quaternions and the octonions, because there are quite some interesting problems, and then talk about what are the phenomena, new problems that arises when one moves from rank 1 to higher rank. There are new features there that's also quite interesting. So that's my plan for today. And so let's start with the quaternionic case. When we are in a quaternionic projective, okay, so again, my main aim is to understand the structure of submanifolds which have the same shape at every point, and homogeneous hypersurfaces are the most elementary examples of such submanifolds. Yeah. And so in quaternionic projective space, this is actually the homogeneous hypersurfaces. They are known since quite some time, sometime in the 70s. So there one gets only tubes around certain totally geodesic submanifolds. Yeah, that's quite surprising here. It's much in the quaternionic projective space, classification is much simpler. Yeah, any homogeneous hypersurface arises as a tube around a certain totally geodesic submanifold, namely a quaternionic projective subspace or a complex projective subspace of half dimension, nothing else. Yeah, it's a very short list. Then the number of distinct principal curvatures for these homogeneous hypersurfaces, if one is diligent, one can calculate these, and it's just 2, 3, and 4 which arises here in this situation. So it's probably something one would expect, only small numbers from what we saw yesterday. So then there is the question, is every hypersurface with constant principal curvature necessarily homogeneous? Yeah, that's the natural question to ask in this situation. And of course the simplest case is that one wants to study if there is just one constant principal curvature, but this is a consequence of the Kodazzi equation that there is no such hypersurface, and that was first written down by Martinez and Paris, I believe. Interesting case is then G equal to 2. That's really where something happens, and Martinez and Paris, they did some calculations, and it turns out that one gets only homogeneous hypersurfaces. And in this case, I think it's just the case when k is equal to 0. So a tube around the 0-dimensional projective space, that's just a point. So it's a sphere. Yeah? So a sphere in quaternionic projective space has 2 distinct constant principal curvatures. That's what one gets in the G equal to 2 case, and nothing else. So just the spheres. And that's it, basically. But then I investigated this problem, and I came across something. I was surprised. You remember this curvature adapted, which I introduced yesterday? The curvature adapted hypersurface is curvature adapted if the shape operator and the normal Jacobi operator commute. Yeah. This was in complex projective space, or in general in complex projective space, equivalent for the hypersurface to be a Hopf hypersurface. Yeah? This was the characterization of Hopf hypersurfaces using not the complex structure Yeah? So if one investigates this, it turns out that if this algebraic condition is satisfied, the hypersurface must be homogeneous. Now that was quite surprising, since this algebraic condition implies homogeneity. Yeah? So in particular, it implies constant principal curvatures. This is it's quite some complicated calculations using Gauss and Codazzi equations, which lead to this conclusion. In quaternionic hyperbolic spaces, the situation is more complicated and I think also more interesting. What happens there is the homogeneous hypersurfaces are not yet classified, and I will talk in a minute about what the remaining problem is. So we could reduce it to a linear algebra problem, which we cannot solve. But there is a partial classification, which I got with my collaborator Hiroshi Tamaru. So G equal to 1 is impossible in the hyperbolic case, and one can do very similar calculations to the projective case, also in the hyperbolic case, in the case of two distinct principal curvatures. Ortega and Paris did this, and they found out again it's only the spheres in the hyperbolic spaces which arise in this situation, so which have two distinct constant principal curvatures. And that's not true. There is also the horospheres. Yeah. So this is known. And also, and then I looked at this, the corresponding problem when one imposes curvature adapted in the hyperbolic situation. But these equations become more complicated in the hyperbolic case, surprisingly, and I could prove homogeneity only under the additional assumption of constant principal curvatures, which is of course a strong assumption. Yeah? I still believe that this assumption is not necessary, but cannot prove it. Yeah? So there is quite similar results between the projective and hyperbolic case, but there's a little bit of a few open problems. And I want to describe what the situation is with the homogeneous hypersurfaces, where we got stuck, why we can't classify them. The setup for classifying homogeneous hypersurfaces is pretty similar to what I described yesterday with the complex hyperbolic space. One uses the description of the hyperbolic space as a solvable Lie group with a suitable left invariant Riemannian metric, and this is a consequence of the Iwasawa decomposition of the isometry group. Yeah? Whenever we have a non-compact symmetric space, the isometry group is a non-compact real simple Lie group, and then one gets an Iwasawa decomposition and one can start with all this theory. Yeah? So when one does this in this particular case, so you see here we have the isometry group of quaternionic hyperbolic space, so it's a symplectic group SP1N of signature 1. The stabilizer is SP1 times SPN. I think so, yeah. So we write this space as G over K, and then on Lie algebra level we get the Iwasawa decomposition. So this is the Lie algebra of the stabilizer K, SP1 plus A. This is an abelian subalgebra. N is a nilpotent subalgebra, which in this situation is a generalized Heisenberg algebra with a three-dimensional center, and the orthogonal complement of the three-dimensional center V is a quaternionic vector space of dimension n-1. Yeah, so this is the algebraic structure of the nilpotent algebra arising in the Iwasawa decomposition. It's quite well known. Yeah, that's a generalized Heisenberg algebra which has been well studied. And when we exponentiate, we get, of course, the Iwasawa decomposition on group level. G is K times A times N. And you see when we factor, we divide through K. G over K, which gives the quaternionic hyperbolic space, is equal to A times N, and this is because all the isometries fixing the point are in K, so this acts simply transitively on the space. So we get this solvable Lie group acting on the manifold in a simple transitive way. So then we can move the Riemannian or the Riemannian metric which we have at one point by a times n to any other point, and we get this left invariant metric which gives the quaternionic hyperbolic space. Yeah? So this is the model which one uses for the investigation. And the orbits of the nilpotent group N in the Iwasawa decomposition, these are the horospheres in quaternionic hyperbolic space. That's their geometric significance. And now what we do is to construct homogeneous hypersurfaces. We choose a one-dimensional subspace L in V in the orthogonal complement of the center in the nilpotent algebra. Yeah. So then, using the algebraic properties of the algebra, it is not difficult to show that when we take A plus and then the orthogonal complement of L in V plus Z, what we get is a codimension 1 subalgebra of A plus N. And then so it's a codimension 1 subalgebra. Now A plus N, when we exponentiate, we get the group A times N, which is just the hyperbolic space. When we get something of codimension 1 in here, that of course acts with cohomogeneity 1 on the manifold, or the orbits of this will be codimension 1 submanifolds, so they will be hypersurfaces. Yes, the orbits of the group which we get when we exponentiate this algebra must be homogeneous hypersurfaces. Yeah? And this actually, there is exactly one minimal orbit, and then all the other orbits are just the equidistant hypersurfaces. Yeah? When one would do the corresponding construction in real hyperbolic space, what one would get is a totally geodesic real hyperbolic hyperplane and the equidistant hypersurfaces. Yeah? This is, if one does this algebraic construction in the real case, that's what one will get. Yeah? So it's just imitating this. But this is, of course, is not totally geodesic, but is minimal. And what we could prove is that every homogeneous hypersurface in a quaternionic hyperbolic space which does not have a focal point is congruent either to a horosphere, which arises here through the action of N, to the minimal hypersurface S, which we constructed here, or to one of the equidistant hypersurfaces, yeah, which are equidistant to S. Yeah. So the homogeneous hypersurfaces without focal points we can classify through this construction. So the remaining question is, what about homogeneous hypersurfaces which have focal points? Yeah, we know there are some, like the tubes around quaternionic hyperbolic subspaces. Yeah, these are focal sets, these quaternionic hyperbolic subspaces. So we know there are some. But how do we get all of them?
According to the region, how become minimal hyperspace?
One can calculate the shape operator quite easily, because this is a Lie group. One takes a codimension 1 subgroup, and there is a straight. You see, when one has a Lie group with a left invariant metric, it's quite elementary to write down the Levi-Civita connection, and then you write down the Weingarten equation, and you get straight away that this is minimal from these equations. So it's just the basic theory of Lie groups with left invariant metric. Yeah. So let's assume now we have a homogeneous hypersurface which has a focal set. So then geometrically the hypersurface must be a tube around this focal set, yeah, around this submanifold. So what we then can prove is that this focal set is congruent to an orbit of a group which can be constructed in a similar way as the hypersurface S that I just constructed. We take this, we take our Lie algebra A plus N. So remember, n decomposes into the center and the orthogonal complement. Now in the orthogonal complement V, what we choose is a subspace with constant quaternionic scalar angle and take the orthogonal complement of that. Now what is a subspace with constant quaternionic scalar angle? Suppose first we are in a complex vector space Cn, and we take in there an arbitrary subspace V, not necessarily complex, just an arbitrary subspace, linear subspace V. So here is our subspace V. So then let's take a vector in there, say a vector V in V, and then because we have a complex structure here, we apply this complex structure, we get a vector JV. Yeah? Now this vector JV will have an angle will make an angle with our vector space V. Yeah, so what we get is an angle. Well, this is not necessarily, so if we take here the projection of to this, so here we get an angle, that's right, this is the angle between JV and the vector space V. This is called the scalar angle of V. Yeah? So when one chooses a vector V in the given subspace, applies the complex structure, this determines a specific scalar angle. Now, one says that the subspace V has constant scalar angle if this angle is independent of the choice of the vector V. Yeah? So for example, if we choose a complex subspace V, complex means it is invariant by the complex structure, so JV will always belong to the subspace, so this angle will be 0. Yeah? So a complex subspace has constant scalar angle 0. If we choose a real subspace, we take a vector, apply J, then this vector will be perpendicular to the subspace. Yeah? So a real vector will have constant scalar angle pi over 2. Yeah? So complex subspaces and real subspaces are special examples of subspaces with constant scalar angle. Yeah? But for every value between 0 and pi over 2, one can find subspaces which have a constant scalar angle of that value. Yeah? So this is, for complex vector spaces, what a scalar angle is. Now what I do here is I say constant quaternionic scalar angle. Now we are in the quaternionic situation. Now on a quaternionic setup, we have 3 complex structures, I, J, and K, or in quaternionic hyperbolic space, they come from the quaternionic scalar structure. Yeah? So we have 3 mutually orthogonal complex structures. In fact, we don't have just 3, we have a 2-dimensional sphere of complex structures. Yeah? Now for each such complex structure in the quaternionic scalar structure of this space, we can define a scalar angle. Yeah? Every complex structure in the quaternionic scalar structure of AFHN turns this into a complex vector space, turns the tangent space into a complex vector space, so we can talk about the scalar angle. Yeah? So now we get a 2-sphere of scalar angles. Yeah? And this notion so for given subspace we get a 2-sphere of scalar angles, but the dependence of the scalar angle on the 2-sphere is continuous, so that we will get, since the 2-sphere is compact, we will get a minimum and a maximum for these scalar angles. Yeah? So we can choose complex structures in the quaternionic structure such that the scalar angle becomes minimal and maximal. Yeah? And then these two determine a third complex structure which determines a third scalar angle, and this is then what is a quaternionic scalar angle. Yeah? So it's a triple of scalar angles. Yeah? So I'll give you some examples, maybe. Let's come here. You see, this is our problem where we get stuck. Classify the subspaces of a quaternionic vector space with constant quaternionic scalar angle. So I give some examples. We are now in a quaternionic vector space. And this is the triple of angles. So we are in a complex vector space. So let's say Hn. I'll say Hn minus 1. See, and then when we take in here a k-dimensional quaternionic subspace, what are these scalar angles? Well, whatever complex structure we choose in here, in the two-sphere of complex structures, see, this will be invariant under this. Yeah? So every scalar angle will be equal to 0. So that's where we get 0, 0, 0. Okay? That's my thing. So another example, 0, 0, pi over 2. Oh yes. So this is just a three-dimensional subspace. So we choose an arbitrary vector in a quaternionic vector space, and then take the three-dimensional vector space, which is spanned by, if we apply all these complex structures to the vector v, yeah, the imaginary part of the quaternions applied to the vector v. So this has a scalar angle 0, 0, and pi over 2. So another example will be if we take a complex subspace Ck in a quaternionic vector space. Yeah. So there will be one complex structure in here which leaves this invariant, and the orthogonal complex structures map the Ck into its orthogonal complement. Yeah, that's why we get as the angles 0, pi over 2, and pi over 2. Yeah. Or pi, we get also these. We could take in Hn minus 1, a real subspace. Then every complex structure in the here for H, so this quaternionic vector space, maps the real subspace into the orthogonal complement. So all scalar angles are pi over 2. Yeah? And there are some more possible scalar angles, like phi, pi over 2, pi over 2. Phi is an arbitrary number between 0 and pi over 2. So what we take here is a subspace with constant scalar angle in a complex subspace. So we take in here, in this complex subspace, a subspace with constant scalar angle. And this will then have angle phi, pi over 2, pi over 2 in here. Yeah, which is pretty straightforward. Or finally, we can also realize the angle 0, phi, phi, so constant scalar angle phi. So what do? We take, again, a subspace with constant scalar angle in here, in this complex vector space, and then view the quaternionic space as complexification of the complex one, and complexify the given subspace. So what we get is the angle 0, phi, phi. Yeah? So for each choice of such a subspace, we can produce a homogeneous hypersurface through this algebraic construction, which I mentioned before, yeah, coming from the Iwasawa decomposition. So each choice of such a subspace leads to a homogeneous hypersurface in quaternionic hyperbolic space. The problem we have, which we cannot solve, is classify all the subspaces of a quaternionic vector space with constant scalar angle. These are all examples which are known to us. We can show that for certain combinations of angles there exists no such subspace, but we can't determine all of them. Yeah, it looks like it's a problem from quaternionic linear algebra, but for us it's extremely difficult to solve. So that's where we are with the classification. Yeah. So the questions, I want to summarize the questions which I raised here. So all known hypersurfaces with constant principal curvatures in quaternionic projective space are curvature adapted. Is this true in general? If the answer is yes, then we know what all hypersurfaces are with constant principal curvatures, because we have the classification of curvature adapted hypersurfaces. Yeah? So it would be nice if one could show that constancy of principal curvatures implies that these two operators commute. Yeah, and somehow I have the feeling we're close to this. This may be true. But it is somehow, it is not so easy to use a local argument, because it is not true in the quaternionic hyperbolic space. The second problem is that all known hypersurfaces with constant principal curvatures in these quaternionic space forms are homogeneous. Is this true in general? These are the only known examples, the homogeneous ones. Then all known curvature adapted hypersurfaces in quaternionic hyperbolic space are homogeneous. Is this true in general? I mean, it's true in the quaternionic projective space. Yes. And then that's also an open problem. Classify the hypersurfaces with three distinct constant principal curvatures in both, in the quaternionic projective space and quaternionic hyperbolic space. Yeah? In the complex space forms, this was done by Takagi and me and Carlos, but I don't think this is known in the quaternionic cases. The reason this hasn't been achieved yet, I believe, is that the equations one gets from Gauss and Kodazzi, they are pretty complicated and they're difficult to master, really. Yeah? But that's probably the next step to investigate. And then finally, classify the homogeneous hypersurfaces in a quaternionic hyperbolic space, or equivalently, what I just described here. What one needs to find is all the subspaces with constant quaternionic Kähler angle in a quaternionic vector space. Yeah, so that's the equivalent problem. And so there are a number of interesting open problems in the quaternionic space forms. Okay. Then the next step, yes, very little has been done about the Cayley projective plane and the Cayley hyperbolic plane. You know, these projective spaces, they exist only in dimension 2, octonionic dimension 2. This is because of the non-associativity of the octonions. Yeah, one can't define projective spaces and higher and hyperbolic spaces of higher dimensions over the octonions because of the non-associativity of this division algebra. So there are only these planes. The real dimension of these planes are 16. Yeah? So these are, the octonions have real dimension 8. So when we build a plane over them, is 2 times 8, which is 16. That's the real dimension. Now, the reason one gets all these nice results in complex and quaternionic space forms is that we have a nice geometric structure of them. In the case of complex projective space and complex hyperbolic space, we have a Kähler structure, or this complex structure J, yeah, which helps. In the case of quaternionic projective space and quaternionic hyperbolic space, we have the quaternionic Kähler structure, yeah, this triple of mutually orthogonal complex structures, J1, J2, J3. Yeah? And this helps to do calculations in these spaces. There is no analogon for this. You see, one would like to have, like the octonions, they are, as an algebra, they are constructed through 7 complex structures which are related in a certain way. Yeah, and one would like, then, when one has this at one point, what one would like to do is, like in the complex and quaternionic space, move this around to other points on the manifold such that this is invariant under parallel translation. But unfortunately, the topology of these spaces doesn't allow us to do this. Yeah? It's impossible. So there is no sensible or no reasonable octonionic structure on these projective and hyperbolic planes. And that makes it difficult to do explicit calculations. I mean, what one can do still is one can classify the homogeneous hypersurfaces. Iwata did this in the projective case, and I did this with Tamaru in the hyperbolic case. So that's still possible, and that's possible because one knows the isometry group, and one can reduce the problem to some group theoretical problem, and one uses structure theory of semi-simple Lie algebras to solve the problem. Yeah, so that's possible still. So these are all known, homogeneous hypersurfaces. But one can also calculate the number G for homogeneous hypersurfaces in the projective plane. So this is either 2, 3, or 4. That's not too difficult. But in the hyperbolic case, I think it's already too complicated. That hasn't been done yet. So the general problem is find a good approach to study hypersurfaces in these two types of planes, yeah, in the projective and hyperbolic plane over the octonions. See, one remarkable thing is the curvature tensor of these projective and hyperbolic planes is known. There is a nice explicit formula which was derived by Brown and Gray. Yeah? So there's an expression for the curvature tensor, and once one knows the curvature tensor, one can do some calculations using Gauss and Kodazzi equations. Yeah? But I don't think anyone has really made a thorough attempt to do this, including myself. So, yeah, so I think there is something one can do in this direction. So it's only little is known about these two spaces. So what I've described now, or what I discussed, is what is known in the rank 1 symmetric spaces. These are just the projective and hyperbolic spaces over the normed real division algebras and the spheres, of course. And now I want to move to something more complicated, symmetric spaces of higher rank. Now, when we have a symmetric space, the rank of a symmetric space is the maximal possible dimension of a flat torus or Euclidean space which can be embedded totally geodesically in the symmetric space. Yeah, in a sphere, the maximal dimension of a flat totally geodesic submanifold is 1. Yeah, it's just a circle. You can't have something flat and higher dimensional in a sphere which is totally geodesic. You know, the totally geodesic submanifolds in spheres are all these spheres, and they have positive curvature, so you can't get anything flat. So in a sphere the rank is 1, and that's similar in projective spaces and in hyperbolic spaces. So higher rank symmetric spaces, the most prominent examples of higher rank symmetric spaces are the Grassman manifolds of k-dimensional subspaces of some real complex or quaternionic vector space, and then the non-compact dual spaces. Yeah, so this somehow makes Grassman manifolds as quite good objects for study for the problems we discussed so far. It's quite natural now to move to Grassman manifolds as a next step. Now, what is the problem that arises there? The difficulty is that different tangent directions are not congruent anymore. See, when we are in a sphere, so imagine a sphere, there is a nice property which we often use without actually thinking about this. Yeah? So when we take two tangent vectors of the sphere, say here is a tangent vector and there is a tangent vector, so both are tangent and both have the same length, there exists an isometry of the sphere mapping this point to that point. That's of course clear because it's homogeneous, but also we can map this tangent vector to that tangent vector. Yeah? And that's a very nice property of the sphere. This property holds also for all the other projective spaces and hyperbolic spaces. It's known as two-point homogeneity of the space. Yeah? But this is no longer true in symmetric spaces of higher rank. So for example, in Grassman manifolds. Grassman manifolds are homogeneous, so you can still map one point to any given other point, but it is no longer possible to map any tangent vector to any other tangent vector of the same length. Yeah? And that makes it more complicated in Grassmannians or in general in symmetric spaces of higher rank. Yeah? So one loses this nice geometric property. And the tangent vectors, when we are in higher rank, some of them are what is called singular, and most of them are what is called regular. I mentioned that the rank of a symmetric space is defined through well, let me talk about the complex two-plane Grassmannian, yeah, which is a popular object for study here in Daegu. Yeah? So this is a symmetric space of rank 2. So the maximal possible dimension of a flat totally geodesic submanifold in this Grassmannian is 2. Yeah? And it is a two-dimensional torus which can be embedded totally geodesically in here. Yeah? Now, so when we have the Grassmannian here, so here is our Grassman manifold. See, this is always my picture of a manifold. They all look the same, but yeah, so we take an arbitrary tangent vector. There exists always a two-dimensional torus, totally geodesic, in this Grassmannian, such that this tangent vector is tangent to this torus. Yeah? So we can find a torus in here. So here is a T2. Actually, it's a bigger, so it should be two-dimensional, this T2, such that the given vector is tangent to this torus. Yeah? So every vector has this property. For every vector, we can find such a torus. Now, for most vectors, for most tangent vectors, this torus is unique. There is exactly one such torus. Such tangent vectors are called regular. But there are some tangent vectors of the Grassmannian where this torus is not unique. Yeah? One has actually, there's a large variety of such tori which one can embed in the Grassmannian, to which this vector is tangent. And such vectors are called singular. Yeah? And this difference between regular and singular tangent vectors, that's important for studying the geometry in these spaces. Okay? So the general problem one has is find a good approach to study hypersurfaces in symmetric spaces of higher rank. That's something I'm working on. I'm investigating special cases, like for the complex two-plane Grassmannian with Professor Su. We're investigating some geometric problems. This is good because this is really a toy model. One can try to understand general phenomena just by looking at this two-plane Grassmannian, and then think about this and see what actually makes it work, and try to generalize it then to arbitrary symmetric spaces. Yeah? And there are also interesting new features that arise there. Here, I'll give one example. Here is an example of a symmetric space of non-compact type. It's a 9-dimensional manifold. It's SL4R over SO4. So this can be realized as the set of all upper triangular matrices with real coefficients and determinant 1. Geometrically, this is the set of all, this symmetric space geometrically is the set of all Euclidean structures on a 4-dimensional vector space. Yeah? If you have a 4-dimensional vector space, you can put on a Euclidean structure, and then all these Euclidean structures, you see when you apply an element of SO4, you preserve all the angles and you preserve all the distances, Yeah? So the stabilizer at the point of a Euclidean structure will be SO4, and the SL4R moves around all these Euclidean structures. It moves one to another one, and so. So this is a symmetric space. And we take in there two hypersurfaces. And it's a very elementary construction. See, these give us coordinates on the manifold here, these xij's. So what we do is, you see this, we just put, here in this case, we put one coordinate equal to 0, x12 equal to 0. What we get is, of course, a hypersurface. Yeah, we just put one coordinate equal to 0. And here, we put the coordinate x23 equal to 0. We get another hypersurface. Both are homogeneous hypersurfaces. One sees this from the construction. Yeah, so these are two homogeneous hypersurfaces in this symmetric space. And it's quite remarkable that these two homogeneous hypersurfaces have the same principal curvatures and the same multiplicities, but they are not congruent to each other. So there is no isometry of the ambient manifold of SL4R over SO4, which maps P1 to P2. Yeah? So the new phenomenon we have here is there can be homogeneous hypersurfaces with the same principal curvatures and the same multiplicities, but they are not isometrically congruent to each other. Yeah, in rank 1, this phenomenon does not exist. Yeah? When you have, I mean, the principal curvatures and their multiplicities, they characterize the homogeneous hypersurface. Yeah? So that's a new phenomenon that arises there. Another interesting thing, it's something I investigated with Professor Su here, is horospheres in hyperbolic Grassman manifolds. So let's consider the hyperbolic Grassman manifold of the two planes in Cm plus 2 with the signature 2 metric, standard signature 2 metric. So what do we want? Positive definite two planes in this particular complex vector space with this indefinite metric. Yeah? So this is a non-compact symmetric space of rank 2, and it also has an Iwasawa decomposition because this is a non-compact real simple Lie group. Yeah? Whenever we have such a group, we have an Iwasawa decomposition. And you see again here, what we can do is we can realize this Grassman manifold as a solvable Lie group equipped with a left invariant Riemannian metric. Yeah? This setup always works, also in the higher rank case, which is quite useful. Now this, when we look at the stabilizer here, the action, if we take the adjoint action of SU2 on the tangent space, this gives us a quaternionic structure, and because of parallelity, we can move this around, move to any other point on the manifold. That's K invariant, this structure. So we can move this to any other point of the manifold, and what we get is a quaternionic Kähler structure. Yeah? And what we also can take is here R. So we take the adjoint action of R. This gives us a complex structure on the tangent space at a point, and by K invariance, we can produce through this a Kähler structure on the manifold. Yeah? So these two objects here in the stabilizer, so the adjoint action, they produce two geometric structures on the manifold, a Kähler structure and a quaternionic Kähler structure. Yeah? And that is quite, this particular Grassman manifold is quite unique in this respect, because the only manifolds which have Riemannian manifolds, which have a Kähler structure and a quaternionic Kähler structure, and they're really different, so the Kähler structure is not part of the quaternionic Kähler structure. It's just this Grassmannian and the corresponding compact one. Yeah? There are no other ones. Yeah? So it's a manifold which has a rich geometric structure, complex structure and a quaternionic structure. Now we pick in here a horosphere, P, a horosphere in the manifold. It's quite easy to construct it geometrically. you see, in the hyperbolic cases that I discussed before, the horospheres always arose through the action of the nilpotent group in an Iwasawa decomposition. Yeah? But now here we have higher rank. Higher rank means that so A in this here we have rank 2, so A is two-dimensional. So the codimension of n is 2 in A plus n. So the action of n, or the codimension, or the what did I say? The codimension of a principal orbit of n is 2. Whereas a horosphere is always a hypersurface. Yeah? So the orbits of n do not give horospheres anymore. Yeah, but what one needs to do here is one has to remove a one-dimensional subspace from the abelian part and then add the nilpotent part, and what one then gets is the horosphere. And this is how it works for this particular Grassmannian, and this is the general construction also in higher rank symmetric spaces. Yeah? And what we could prove is that when we have a horosphere in this Grassmannian, then the following statements are equivalent. This vector xi, which we removed, is a singular tangent vector. See, what is the geometric picture we have? Remember in my talk yesterday, I explained how to get a horosphere. Well, we start off with a point and a geodesic ray. Now the point is that's the point where we maybe take the stabilizer as a point O in the manifold, and then here we have our tangent vector, which is xi. Yeah, this determines the geodesic, which goes to infinity, and the horosphere is obtained by, we take all these spheres here, which pass through this point, and where the radius is on this geodesic ray, and then the radius tends towards infinity. This is how we get the horosphere. Yeah? Now, this vector xi can be regular or singular. Yeah? I mean, that's what I explained before. We have regular tangent vectors, singular tangent vectors. So there are different types of horospheres. Those which are given through a regular tangent vector, those which are given through a singular tangent vector. And the ones which are given through a singular tangent vector can be characterized by the property that the maximal complex subbundle of the tangent bundle of the horosphere is invariant under the shape operator. Yeah? And this is also equivalent to saying that the maximal quaternionic subbundle of the tangent bundle of the horosphere is invariant under the shape operator. You see, we have these two geometric structures, the Kähler structure and the quaternionic Kähler structure. They naturally induce the subbundles of the tangent bundle of a hypersurface. Yeah? And it's just the simple property of invariance by the shape operator characterizes the singular tangent vectors, which is quite a nice characterization of the horospheres which are singular, or in general of singular tangent vectors. Yeah? So the problem is, find a similar characterization of, say singular horospheres in symmetric spaces of non-compact type. See, here we use this, the fact that we have a complex Kähler structure and a quaternionic Kähler structure. But there should be something in general in symmetric spaces of higher rank, of a similar kind of thing, similar geometric structure which one can use to characterize the singular tangent vectors. Yeah? So that's an interesting problem. Another result we obtained is, now I go to the compact case. So we take a hypersurface in the compact complex two-plane Grassmannian. Then both these subbundles, the maximal complex subbundle and the maximal quaternionic subbundle of the tangent bundle of the hypersurface, are invariant under the shape operator if and only if the hypersurface is congruent to one of these two types of tubes. Yeah? So we get a tube around a totally geodesic Grassmannian of just one lower dimension here, or a tube around a quaternionic projective subspace embedded in the Grassmannian, which happens only in the case that M is even. Yeah? So again, there is a nice characterization of particular type of hypersurfaces through these geometric structures which are given on the manifold. Yeah? The problem is, find the generalization of this to symmetric spaces. Yeah? So use the geometry of a symmetric space to get a similar characterization. So I want to, where am I? The homogeneous hypersurfaces in symmetric spaces of higher rank, they are classified in the compact case by Colros. Well, I should say it's only if we assume that the symmetric space is simply connected and irreducible. There are always these subtleties. If we don't assume it's simply connected, one has to look at covering groups, and if the space is reducible, there are some additional problems. Yeah? And the non-compact type, they are. Well, we have now partially classified them. So in fact, I think we have a conceptual approach now for classifying homogeneous hypersurfaces in symmetric spaces of non-compact type. And maybe I explain how this works. So this is a result from this year. So assume that we have a group acting on a symmetric space isometrically, symmetric space of non-compact type isometrically with cohomogeneity 1, which means that the generic orbit has codimension 1, so the generic orbit is a homogeneous hypersurface. Yeah? Classifying homogeneous hypersurfaces is equivalent to classifying cohomogeneity 1 actions. Okay? So then one of the following statements holds. Either the orbits form a Riemannian foliation on the manifold, and these we could all classify. So that's we already did 6 or 7 years ago. So for every symmetric space of non-compact type, we can write down all possible homogeneous hypersurfaces which have no focal points, because this is exactly what this means. Yeah, that we have a foliation on the manifold by codimension 1 submanifolds is equivalent to saying that all these submanifolds do not have any focal points. Yeah? So this is the classification of homogeneous hypersurfaces with no focal points. Or there is a totally geodesic singular orbit. So these are homogeneous hypersurfaces which are tubes about totally geodesic submanifolds. Also there we can write down a complete list that we finished about 5 years ago. The problem was, what are homogeneous hypersurfaces which have a focal set which is not totally geodesic? That caused us a lot of headache. And for this have we produced then this conceptual approach, and there are 2 ways to get such homogeneous hypersurfaces. One is the action of H is orbit equivalent to the canonical extension of a cohomogeneity 1 action on a boundary component of M. Now, let me say first, what do we mean by canonical extension? When we are in R3, and in R3 we take a plane. So here we have R2. So let me take one particular type of homogeneous hypersurfaces. Let's say we take a point and then all the spheres centered at that point. Yeah, so these are homogeneous hypersurfaces in a plane. Here these circles, yeah? So they come just through the usual rotation through this point, an SO2 action. Yeah? And this action we can extend canonically to R3 by just adding the translation in the perpendicular direction here. So what we get now is here we get a line, and there we get the cylinders. Yeah? So you get the action on R3. So here we get homogeneous hypersurfaces, the cylinders, which are homogeneous through a canonical extensions of the circles in the plane. Yeah? It's quite a canonical construction. And this is what we mean by canonical extension. We produce the homogeneous hypersurface from a homogeneous hypersurface on a particular type of lower dimensional totally geodesic submanifold. Yeah? This is what we mean by canonical extension. And this particular type of totally geodesic submanifold refers to the boundary component of M. And the ones we take here are those which were constructed by Satake in the maximal Satake compactification of a symmetric space of non-compact type. So what Satake is, he took the root space decomposition of the Lie algebra of the isometry group, and then particular choices of roots leads to particular totally geodesic submanifolds in the symmetric space, which he then pushes to infinity to compactify the space. Yeah? And it's these, so these are totally geodesic submanifolds of lower rank, so symmetric spaces of lower rank. So what this construction gives us, somehow it gives a rank reduction. Yeah? So if we are on a rank 3 manifold, through this we can reduce it to rank 2, and from there to rank 1. So basically we need to know only those homogeneous hypersurfaces on rank 1 spaces. From there we can go to rank 2, from there we can go to rank 3, and so on. Yeah? So what this gives us is a rank reduction, and it just boils down to classifying them on rank 1 spaces, and there is some other problem. And the fourth one is, it's the homogeneous hypersurface is obtained by a certain construction using nilpotent algebras. And that's a bit complicated, this algebraic construction, and I don't want to explain this here. But I want to mention, to finish off, what are these open problems to classify all the homogeneous hypersurfaces. One is, see, I said we reduce this problem by rank. Now sometimes this boundary component can be a product of two manifolds. And the problem is we don't know what are homogeneous hypersurfaces in products of manifolds. Take this simple example, a product of two real hyperbolic planes. And I think it is still not known what are the homogeneous hypersurfaces in this four-dimensional manifold, a product of two real hyperbolic planes. Yeah? So this is the problem which we cannot solve yet. Yeah? Classifying homogeneous hypersurfaces in products of spaces where we know of course the homogeneous hypersurfaces in each of these planes, but we don't know how to construct those in the product. Yeah? So this is the problem we are stuck with for the canonical extension. And for this nilpotent construction, see, I didn't explain how this works, but the remarkable thing about this is we can only construct two examples. See, when you produce a method for produce a method for constructing homogeneous hypersurfaces, you would like to get many examples to this, but we get only two. But it is essential that we get these two because we can't get them through any of the other methods which I described in the theorem. And amazingly, these two examples, these homogeneous hypersurfaces, arise only in two symmetric spaces related to the exceptional Lie group G2. This 8-dimensional symmetric space, G2 2 over SO4, and this 14-dimensional symmetric space, G2, the complex Lie group G2 over the compact subgroup G2. Yeah? So the fourth method, which I didn't explain how it works, so far leads only to these new examples, and we went through many other symmetric spaces, and we can show there exists no other examples to this, but we can't prove it in general. But we believe there are no other examples. Yeah, so this is where we are at the moment with the classification of the homogeneous hypersurfaces. I think I should stop here now. Thank you for your attention.
Thank you.